Welcome to note set number 32, where we'll start our discussion of design of IIR filters. So this will cover up, section 10.3 up through 10.3.2. The next set of notes will pick up where that leaves off and start with 10.3.3, where we'll see kind of the main way of designing IIR filters. So in this set of notes, we'll just kind of introduce the idea, some of the issues, talk about a couple early attempts at doing this kind of design, see what the problems are, and set the stage for the main method, which is called bilinear transform. So just a little bit of motivation. So DSP was kind of first developed in the really in the 60s. I mean, there was some initial theory earlier than that, but really in the late 1960s, early 70s is kind of when it was really being developed as a main research topic. And at that point, people had been designing analog filters using resistors and capacitors and sometimes inductors for decades and decades and decades. And so that was a pretty well settled methodology. So there were entire books on how to design analog filters, and virtually every EE student learned how to design analog filters, so that it was kind of an ingrained thing. Today, it's probably not likely that that you learn much about analog filter design. But all those early DSP researchers, they knew all about this, and basically what they wanted to do was exploit what they already knew. So the goal was to take these analog filters, which have infinite duration impulse responses, and they had rational transfer functions, so they mathematically looked very similar to the kinds of things that we wanted. The only difference was S's versus Z's, but careful, that's a huge difference, as we'll see. That's kind of the crux of this issue, is the difference between the S-plane and the Z-plane. So the S-plane, remember, has the J omega axis dividing left half plane and right half plane, and poles have to be in the left half plane for stability. The frequency response lies above the J omega axis, whereas on the Z plane, our frequency quote-unquote axis becomes the unit circle, and that's what accounts for the periodicity of TFTs, and that unit circle is the dividing line on the Z plane, in the same way that the J omega axis is the dividing line on the S plane. So for stability, we need poles inside the unit circle, and so the basic topography, so to speak, of the Z plane for digital filters is very, very different. But nonetheless, there were enough similarities that made the early researchers say, could we somehow exploit these books and books of analog filter design ideas to come up with a way to convert existing analog designs, which are necessarily IIR, into some usable and appropriate discrete time IIR designs. And so, since there's three ways to describe a system, whether it's continuous time or discrete time, there's basically three paths that we can take to try to convert an analog filter into a discrete time filter. So we can look at the three different ways of describing a continuous time system: differential equation, impulse response, and transfer function. Now, from transfer function, obviously, we get frequency response, but those are the kind of the key methods. So if we try to convert each one of those into kind of the equivalent of what that is in the discrete time, we have a way of converting a continuous time design into a discrete time design. So is there some way to take the differential equation and do some mapping of it to turn it into a difference equation whose behavior as a filter will mimic the behavior of the original differential equation. Same kind of thing. Can we take the impulse response of the continuous time signal and somehow make it into a filter that has a same kind of impulse response? And then finally, can we look at it from a transfer function point of view, or more precisely from a frequency response point of view, and say, let's look at the transfer function h of s and somehow come up with some matching to get it into h of z. Now you'll notice here that I've left off the superscripts because it's kind of hard to do the superscripts in a text box. I could have done them, but I chose not to. And as it turns out, the first two methods are kind of obvious and were some of the early approaches. And as is typical, the early approaches didn't quite work as well as one would hope for. And so the third approach, attacking it from a transfer function mapping viewpoint, works very, very well. And we'll focus on that, I say here, meaning in the course. In this set of notes, we'll actually briefly look at these two methods that don't work all that well. And then in the next set of notes, we'll look at this transfer function approach. But the basic idea is, given a continuous time filter with, that could be characterized in any of those three ways, somehow convert it through some sort of mapping or process or whatever, manipulation, convert it into a discrete time filter. And what we would like is that whatever passband and stopband characteristics we originally have, so passband edge, passband ripple, stopband ripple, gets carried over into the discrete time filter as closely as possible. We also want to ensure that since all of the designs that we have from our theory, our existing books and books of analog filters, they're all designed to be stable. And so it's desirable to have whatever our process is for conversion to retain that stability, so that if we start out with a stable design, we'll end up with a stable design. And so we don't have to worry about that. And then ultimately, we'd like whatever we end up with to be a physically realizable discrete time system. So it should be causal, obviously. And we've talked about how the things that we implement are basically described by transfer functions that are a rational function. So a ratio of a polynomial in Z over a polynomial in Z. And since discrete time IIR filters can't really make linear phase filters, we won't even focus on the phase. We'll just simply spec the magnitude, make our design, and then check what do we get for the phase. And we'll just see from there and just kind of let it be at that point. Okay. Now, there's going to be a bunch of notation here since we're going to be dealing simultaneously with continuous time things and mapping them into discrete time things. What we want to do is make sure that we've got a good handle on the notation, because the notation is kind of the challenging part here. And we've been wrangling with notation all semester long, or all throughout the course. I don't like Proakis and Montelakis' use of the capital omega for continuous time radian frequency and lowercase for discrete time. I actually prefer them the other way, which is kind of a more classical way of doing it. But here, to help you follow along in the textbook, I will stick with Proakis and Montelakis' use of capital omega for continuous time frequency and lowercase omega for discrete time. But I'm also going to try to stick very carefully with Peratt's superscript notation. So Peratt, remember, is author of another textbook that we're not using, but I keep touting the beauty of his notational system, which I've never seen anywhere else other than in Peratt's book. So he uses a superscript because the capital H is just getting thrown all around in many books, and you don't know what that capital H is representing, and it's very hard to keep it straight. So Peratt uses a superscript L to represent the Laplace transform, superscript capital F to represent continuous time Fourier transform, a superscript Z to represent the Z transform, and a superscript lowercase f to represent the DTFT. Armed with all of that, we'll try to stick with that. So remember, the book doesn't use these superscripts. What the book does is it uses a sub A, which is actually fairly common, to indicate that this is the analog. So that at least gives you an idea of which side of that line we are on. But using the superscripts also tells us whether we're talking about a transfer function or a frequency response, without having to look at what is the argument, whether it's an S or an omega or a Z or an omega. So just keep in mind here that the capital omega here is going to be radians per second, and the lowercase omega is going to be radians per sample. So that'll be the key. All right, continue on here. For IIR design, we'll start with this differential equation conversion. And I don't know for sure about the history, but I'd be willing to bet that this was the first method that was developed. And the reason is that difference equations were originally used as a way of solving, numerically solving differential equations. So that idea was around when researchers started realizing that discrete time systems were basically described in terms of difference equations. So the basic idea is to look at how do we approximate derivatives, and then substitute in those approximates into our differential equation for the system, and that will give us a corresponding difference equation, and we say, okay, that's a difference equation that should behave similarly to a system that had the original differential equation. So if we look at the derivative and we think about how we learned about those in calculus, we learned that they were a change in one variable over a change in the other. So if unfortunately in the discrete time world, our change is can only get as close together in time as one sample spacing. So we can take the signal's value at n and the signal's value at n minus 1, take the difference, and the spacing in time will be capital T. So we're just doing that kind of approximation of a derivative by saying I take a point here, I take a point here, I take this difference divided by this difference, and that gives me the slope of the line between the 2 points. And in calculus, we take the limit as the two on the horizontal axis, the 2 points on the horizontal axis get closer and closer and closer. Well, we can't take that limit. If we take that idea and apply it twice, we take the derivative of the derivative. So taking the second derivative would require taking 2 separated points. So here is the derivative at n, and here is the derivative at n minus 1. and then we're going to divide each of those, that difference by capital T. And if you work that all out and see where the dust settles, you'll boil it down to something that looks like that. And so basically we can do this kind of thing over and over. We can get any order of derivative that we want. And if you've ever studied a numerical methods course in the math department perhaps, that course probably covered these kinds of differences applied to approximating derivatives. So we can then find all these approximate derivatives, substitute them into the differential equation, rearrange all the terms, and put them into our standard form for our difference equation, and bang, we end up getting a difference equation that describes the system, or describes a discrete time system that should approximately behave like the original continuous time system. So that's the idea. Let me back up. So then once we have that difference equation, we can take its z transform and find what its transfer function looks like. So that's what leads us to this or. We can think of it this way, totally equivalent. We can say, well, I've got a derivative, and I know that in the S domain, multiplying by S corresponds to taking a derivative. So this is going to correspond to an S, but in the discrete time world, this corresponds to a 1 minus a z inverse divided by t. So that gives us a way of replacing S by this little equation in z, and so it gives us a way of mapping z to S, well actually the other way around, mapping S to Z. So everywhere there's an S we would replace that. And we could then do the same thing for the second order derivative and recognize that when we get that, that can actually be written as 1 minus Z inverse over T squared. So it's just a square of what we had for S, and in general we can show that S to the K gets replaced by the thing that we had for S raised to the K. So in reality, what we can talk about is a replacement of S, whether we have the K there or not. We can just replace S by 1 minus Z inverse all over T. And so there is our design methodology. You give me an analog filter with a transfer function that I know, show me the functional form for that, a ratio of two polynomials in S. Everywhere there's an S, I replace it by this, so that thing's going to get raised to all sorts of different powers. Work all that out, simplify it down to our standard form for a transfer function in Z, and that will be the transfer function for a discrete time filter that should, to some degree, approximate the original analog filter. So that's one very simple design process that we could do. So to understand what's happening here, we just had S is equal to something in terms of Z. If we solve that for Z, we now get Z is equal to this, and that allows us to see how the S plane gets mapped to the Z plane this way. And so what we can see is that the entire left half plane gets mapped into this circle of radius of 1, diameter of 1 centered at 1/2. So that's kind of an odd thing. We know that in general that the role of the left half side of the plane for the S domain is played by the entire interior of the unit circle. So what we're seeing here is actually that we are mapping the left half side of the plane into some sort of very constrained subset of where it could possibly get mapped to. And notice also, let me get rid of some of this stuff here, that if we have poles and zeros, their locations are going to get mapped according to this. So, you know, I might have some poles way out here, and I might have some you know, zeros here. All those are going to get mapped into this region. So that means I can only have poles in this region. And remember, poles kind of make things pop up. So so I can make my frequency response pop up in this region, but once I get out here, it's going to kind of just die down. Remember, it won't go all the way down to the surface, but because of the air hockey table, but it will tend to sag down. So our stability is preserved because the left half plane maps into the unit circle. But we're severely limited to the kinds of filters that we can actually build, and pretty much it's low-pass filters. So this is not a very good approach, despite the fact that it's kind of soundly based and comes out of a fair amount of early mathematics, but not really well suited to, you know, design of nice discrete time filters. So we then charge on to another idea, and so this idea is called impulse invariance. So the method we just looked at was based upon, you know, trying to convert the differential equation into a difference equation. Now we're going to try to convert the impulse response of the continuous time system into an impulse response that matches it for a discrete time system. So what we're basically going to do is say, well, I see an error that I made here. This should be n times capital T. I'll try to fix that before I post the notes. And so if we set h of n equal to samples of this at some appropriate sampling spacing, capital T, we know from our sampling theory that we end up getting something that looks like this for the frequency response. This is just our standard description of what happens when we sample something. So we get this equation, and this equation is just showing how we get aliasing. So for the k equal to 0 term, we just get this HA term, and here we've converted the HA into the equivalent version of the discrete time frequency. So really we have H sub A of, well, I have it right here. Normally we have H sub A of capital omega, which is in radians per second, but we can make a change to a new variable omega, little omega, which we can think of as being in radians per sample, and we multiply little omega times fs, which is in the units of samples per second. And so if we do a units analysis here, we see that the samples cancel, and we're left with yet another error here, radians per second. So that's how we think about connecting the analog frequency response to the discrete time frequency response is through that scaling. But in addition to that, it's not just a scaling of the frequencies, there's also the aliasing of the frequencies, and so that is captured by this effect of this summation. And so what we're seeing here is that if we were to start off, say for example, with a continuous time frequency response that looked like that, the discrete time frequency response would actually be a sum of these things. So you know, it would come down like this and then kind of scoop up like that. And remember, we only need to know it from minus pi to pi. So this would come down and kind of scoop up like that due to the sum of the aliasing terms. And so that's the basic idea here. You know, this way of thinking about it, plotting this on a capital omega, plotting this on a little omega, just follows this connection up here. So notice that when we know that pi corresponds to fs over 2. Notice that when I let fs, when I let, well, let's do it this way. We know that little omega corresponding to 2 pi corresponds to fs. So when I plug in 2 pi for little omega, I'm going to be evaluating this at 2 pi fs. That's the radian version of, radians per second version of the sampling rate. So this connection makes an awful lot of sense. But now we see that to avoid this aliasing, we really need an original frequency response that swoops down like that so that we don't get too much aliasing happening. So again, we're limited to, you know, essentially low-pass filters and maybe some band-pass filters. And we're also kind of forced to, you know, maybe artificially sample faster than we want just for the design of our filter, let alone, you know, not really for the characteristics of the signal that we're interested in processing. So in a couple methods here that seem to have some serious problems. We want to finish off here, though, just to show that this impulse invariance method does actually lead to a rational transfer function, because it's not clear that that does. All we're doing is we're saying, imagine that we have a discrete time system whose impulse response corresponds to samples of the continuous time filter's impulse response. That does not guarantee that we get a rational transfer function in the discrete time world. But let's ask, you know, how do we do this and guarantee that we get a rational transfer function that still achieves this impulse invariance? So we can answer this easily for the case where our continuous time filter has distinct poles, and you can generalize that. We won't do that in the notes, and the book doesn't do it in the textbook either, but it is possible. So if we have distinct poles, we have a characteristic polynomial in the denominator that can be factored into n, assuming an order n polynomial in the denominator. We can factor it into n, a product of n terms, each one looking like this, s minus pk. And then after we do a partial fraction expansion, that product of terms ends up getting expanded out into a sum of individual first order terms. So, you know, go back and, if it's not clear, go back and take a look at how we did a partial fraction expansion on a Laplace transform, a rational Laplace transform, to convert it back into the time domain. And so when we convert that back into the time domain, we transform each one of these terms, and if you go to your table, you'll see that we get something like that. So the p sub k's are the poles, the c sub k's are the coefficients that come out of the partial fraction expansion. So we now end up getting that the impulse response is just the sum of a bunch of exponential terms. And since we're assuming that the system is stable, all of these poles have negative real parts, so these exponentials will decay down. Okay, so we have a structure that we're assuming, because we're assuming distinct poles. So there's a structure for our analog system, and now we want to impose the impulse invariance condition. So we say that we want some discrete time impulse response h of n, whose values will be equal to samples of this thing. So we just sample that. So we take our t and we sample it, and we get this e to the pk n capital T. And then we just rewrite that over here to get this more into a discrete time form, because discrete time exponentials are some number raised to the n. And if you look on your Z transform table, you'll find this as an entry, and you'll be able to see that it transforms into something that looks like this. Here we've included the C sub k that was out in front of that. And so now, you know, this is just a sum of a bunch of first order terms, and just like we got a sum of first order terms here by doing a partial fraction expansion, if we kind of undo the partial fraction expansion, just find a common denominator and fuse everything together, we'll end up with a rational function. And so this just demonstrates that yes, at least for this case, it is possible and we can generalize it. It's pretty easy to see how we go about doing that. Let me clear some of this stuff off here and just summarize what we've done here. So to impose the impulse invariance method, we just find where the poles are, and then we use those poles in this e to the pk capital T, where T is our sampling interval, and stick that in front of a Z inverse, and we're done. And just add up the terms. Okay, so that's a pretty straightforward way about the design. And here's an example of doing that. So we have some continuous time system that has this as its transfer function. It's already been factored into, or expanded, partial fraction expanded into two terms, which, since the poles are complex, you see that they are complex conjugate poles. And so here is the response of that particular continuous time analog filter. So it's some sort of high pass-ish kind of thing, not entirely high pass-ish, because this kind of does look like it's continuing down. It has a resonant peak, and it kind of falls off quickly as we go down to zero. If we apply this to see what kind of frequency response we'll get under impulse invariance for a couple different t values, we see that we get for two different t values something very, very different. So notice that capital T here of 0.1 corresponds to a sampling rate of 10, and notice that at 10, well, really we should be looking at 5, right? That we're getting quite a bit of aliasing here, and a t equal to 0.5 is even worse. So what we see, not unexpectedly, where the peak resides in discrete time frequency depends upon the sampling rate. That makes complete sense, because how this maps to frequency depends upon the particular sampling rate selected, right? We know that when we do the mapping from discrete time to continuous time, we know that, well, this is normalized frequency, so this corresponds to pi. That's going to map to Fs over 2. So for different Fs over 2s, this frequency, how it maps to physical frequencies, changes. And so all of these will get mapped to different physical frequencies. That's why these spikes are in different locations for different sampling rates. But more importantly, we see that the basic shape of this changes quite drastically. With 0.1, we see that it does continue, it does retain that kind of swooping down to a small value, whereas for 0.5, it doesn't really quite do that. So this is just illustrating that this is it's a semi-viable method, but it has a lot of problems built right into it. It is semi-viable, and there is a MATLAB command for it that's called ImpInvar, and you can read about it. So basically, you give it the B and A coefficients for the numerator and the denominator. You tell it what sampling rate you're going to do, and it comes back with the BZ and the AZ. So those are the coefficient vectors for the Z domain. And then there is some issue down here with whether you have repeated poles or not, and so if you have two closely spaced poles, you may want to be able to say, well, okay, just really treat those as repeated poles. because they may actually be in the same location, just slightly perturbed due to some numerical precision. So anyway, that's the basic idea there. Neither of these two are the premier method. In the next set of notes, we'll talk about the bilinear transform, and that's what kind of is the workhorse of IIR design. So we'll stop there for now, and I'll see you in the next set of notes.